Hello, everyone. Good afternoon. It's great to be here. I'm Santi Adavani, co-founder and CTO of RocketML. We are a scientific machine learning company based out of Portland, Oregon. So today I'm going to talk about scientific machine learning for full field predictions or using PDE or using HPC servers. It's an intersection of two fields, which is laws of physics, which is basically scientific computing, partial differential equations, solving ordinary differential equations, and machine learning. So the idea is, how do you solve some of these forward and inverse problems, which are primarily driven by PDEs and ODEs? Using machine learning is basically the high-level idea of scientific machine learning. So in a little more detail, so this is kind of the spectrum of problems that we generally deal with in any science and engineering fields. On one end of the spectrum, basically when you look at the problems through the lens of data and amount of information, on one end we have scientific computing problems, that is solving PDEs and ODEs using traditional methods, finite elements, finite differences, etc., and where we do not use any ML-related techniques. So no data, no simulation data is used ahead of time. And on the other end, we have machine learning, large-scale machine learning techniques, where we use lots of data, and physics is kind of implicit in solving those problems. So for example, if you generate a lot of simulation data and use neural networks and train them, kind of falls under the rightmost corner in that spectrum. So SciML is basically somewhere in between, where it's a coupled regime, where you're using good ideas from machine learning and also ideas from scientific computing, like finite elements, finite differences, to solve the same problems more efficiently. Okay. There's been a lot of work in this space, a lot of papers in the last few years from both academia and industry, and it has significant implications on solving multi-phase physics problems, control and inverse problems in specific. For example, when you have to solve the same PDE again and again, like typically in control or inverse problems, solving a single PDE very fast becomes important, and having a couple regime techniques would help a lot. So let's ground with an example here, right? So let's say I'm working with solving a Poisson's problem, which has applications in several areas, including electrostatics, flow through porous media, heat transfer, etc. And I'm trying to solve this linear elliptic problem. And what I'm trying to do is I've given a material property, be it permeability, conductivity, etc. I want to solve for my field, in this case, the U of x. And this is a standard problem where I have display conditions on two sides and norm one on all the other. So basically 1 and 0 and norm on all the other. So if you use a typical finite element solver, basically an optimized one, for a 512 cube problem on 2 nodes, it will take around 1200 seconds. The idea is, can we solve this problem in less than a minute? Can we solve this very fast is basically the idea behind using machine learning for this specific case. So there's a lot of work, like I mentioned, in this space. So there are two high-level overarching architectures that are typically used. And one thing I want to emphasize is these methods do not need simulation data ahead of time. So you do not need to run hundreds of simulations to train these networks. So the first one is these are Pointwise architectures. So the idea of Pointwise architectures is you basically, the input to the network is a single point in space-time, x comma y or x comma y comma t, and the output is basically solution at that point. So those are the Pointwise architectures. And these are also called mesh-free solvers, typical pin architecture here. And the pros are that mesh-free, they're faster to train because you can embed a lot of information in small networks. The cons, at least, are you can solve only one PDE at a time. That is, if you change the material properties, you have to train again. And imposing boundary conditions and initial conditions kind of becomes non-trivial. That is, how do you impose exact boundary conditions? What is the factors you use, weights you use to impose them becomes a problem. The second case is our full field architectures. That is, the input to the network is an entire control parameter. That is either a permeability or boundary conditions or initial conditions. The control parameters that you want to use for your inverse problems would become your input data, and the output is still an entire full field solution. For example, the input to the network can be material properties, and the output would be the solution of the PDE. Okay. So that's the key difference. And the pros here are you're solving a parametric set of PDEs. So basically, you're saying, given any control parameter, I want to get the solution in near real time. So you're not solving one PDE, you're solving a parametric set of PDEs. And basically, that enables applications in control and inverse problems, and you can enforce boundary conditions and initial conditions almost exactly using these full field architectures. And the con is training takes a lot of time, and that's one of the things I'll focus on in this talk a little more. So how does it look when you actually put it through a network? Right? So here we are using 3D units, which are popular networks for most of the image-to-image problems. So we do consider this as a 3D image as input and 3D as an output. And we use fully convolutional networks. That is basically 3D convolutions that move around the entire block to give us a solution. And one thing I want to emphasize is because we use fully convolutional networks, these networks are resolution independent. That is, if I can pass in a 64-cube data in it, I can also use a 128-cube data with the same network architecture. It's an important attribute of these networks that we'll continue to use for strategies that we used before. So when I mentioned we can apply exact boundary conditions and bring ideas from finite elements, the main idea here is basically using finite element residuals as loss functions. Okay, so you could either solve a PDE, use that data as your reference for computing the loss, or here we actually use a Gallerican method, use test functions on the nodal values to compute the loss function. So in return, what we are saying is we are explicitly enforcing finite element loss or finite element residual on the loss so that we can train these networks. So basically use finite elements and not generate any simulation data to train these problems. So once you train, I think this is basically one result. Once you train these networks, you can solve the PDE in near real time. So for example, for a given input, obviously the data that the network has never seen, using finite elements, you could get in 1200 seconds, and using the NeuralPDE, you could get the solution in 20 seconds. So that's the advantage you get once you train a network. But the problem is training the network itself. Right? So how do you train this 3D unit so that you can get a NeuralPDE solver that can solve these PDEs faster is a challenge. And that's basically where we have developed some techniques. So this is basically showing the memory, peak memory with respect to the image size or the input volume size. On the x-axis, I have the image size, and the y-axis peak memory. And as probably everybody knows, the GPU memory is limited, and beyond certain image sizes, you cannot fit anything in memory, and you need to scale out. So the peak memory here is not just the model parameters. Generally, the memory also, the contribution to memory is from model parameters, the image sizes, the intermediate tensors the network creates, and the gradients. And if you're using Adam versus Adagrad, it uses more gradients. So it's not just the model that contributes to the memory, it's a lot more than just the model size. So that's the scenario here. So the idea is we scale out. That means we use a large multi-node, multi-GPU HPC cluster to train these networks. So multiple GPUs on single node, multiple nodes connected. And we've developed an in-house distributed data parallel engine for this. We had several problems with Horvath, and other libraries couldn't get solution integrity, convergence problems, performance problems, etc. So we had implemented our own for our users. And the idea of distributed data parallels is simple. You basically distribute your data, you replicate your model, and you do a forward back propagation and do gradient averaging and loss averaging. So our scaling is really good. That is, we scaled up to, or looked at scaling up to 512 GPUs from 1 to 512 on a small, on a network of 4.2 million parameters, and got very good scaling. Even on a very large network, 1.23 billion parameters, we can switch to a CPU cluster and we could see very good scaling here. So this is the underlying engine that we have used for the training. And the results are like this, right? So what I have on the right-hand side is the loss decay with respect to time. And it took us around 34 hours to train this network using 8 GPUs. We just used one. But that's also very slow, right? Training 34 hours is also slow and not very efficient. So we kind of wanted to get a faster technique that basically reduces the time to train, but use the same compute footprint. So that's where we turn to the idea of multigrid. So if you're familiar with some of these linear algebra technique called multigrid used to solve typical PDEs, the idea is simple. That is, you're using a finite element or finite difference method, and you want to solve at a very high resolution. You don't solve the problem completely at that resolution. You basically take a few iterations, use that solution to a coarser grid. You take few more iterations of the finite element or finite difference solver, use it again for a coarsest grid, train completely, and you start using the solution for finer and finer grids. So when you use this kind of a technique, that is multi-level, multi-grid technique, it's been shown that multigrid performs way faster than, say, CG or other methods. You can actually get a solution in order n compute time. So we have used the similar idea here, but applied it for training a neural network. So the idea here is we would start off with a coarse input-output pairs. We would train a network to some few epochs, and we take that network weights and train a network with using higher resolution data, and we further take it down and train it at much higher resolution. So we progressively increase the complexity of the input-output pair resolution as well as the network complexity, and a little more detail. So the way we do it is we start with a smaller network for lower resolution problems, train it, use it as a component for higher resolution problems, add a few more layers, and do transfer learning. And the best combination we got was with half V-cycle. That is, we start with coarse, incrementally increase it to finer and finer grids. And when we do that, this is the kind of loss decay we get. That is, for the same problem, on the same compute footprint, for a 256 cube problem, it took around 2,000 minutes, and on cloud, that's a cost of $735. And using multigrid, we could train the entire problem again in 150 minutes. Basically, it's a reduction of 13 times, and the cost was $55, right? So we haven't changed the compute footprint, used the same footprint, but used a better algorithm to train the network. And when we go for a much higher resolution, so in this case, we went to 512 cube, because 512 cube, we cannot do that on a GPU anymore, we had to switch to a CPU cluster, but we didn't have to start from zero. We could just use the best model from 256 and apply it on a CPU cluster, and we had to run it on for one epoch. Even though it took 6 hours, it could still get a solution in less than 8 hours. And this is a NeuralPDE solver that we could use for getting very high resolution PDE solutions. So in summary, NeuralPDE solvers for real-time PDE solutions can be the future. Like, we can train enough networks with enough control parameters. And full field solvers do not need simulation data for training, and that's an advantage with using finite element losses. You can apply boundary conditions also accurately. And using faster algorithms or fine-tuned multigrid techniques, you can get faster training times. And overall, it can be fast time to solution and very energy efficient methodology that I think the industry can commit to. So with that, thanks for your attention. I'll take questions.
Questions? Wow. Oh.
Thank you for a wonderful talk, Felix Zimmerman, Georgia Tech. It's great stuff for elliptic PDEs, where you also know that these multi-level, multi-grid methods work very well. So I was wondering, maybe there's some seismologists in the audience. So you have waves, so you have hyperbolic systems.
Mm-hmm.
I was wondering whether you could comment on how your methodology would work for that.
So we are working through these problems, incremental complexity. So we start with elliptic problems, and we're working through the parabolic problems now, which would require 4D convolutions. We still yet to look at hyperbolic problems. So the idea is we would use 4D convolutions, and we are seeing promising results that they would work for seismic problems.
Other questions? Nothing. Okay. Thank you very much. Let's thank our speaker. Okay.